Okay, here we go. All right. Okay, normal distribution. By the time we get done, we will hopefully be able to determine whether a data set is normally distributed. We will understand and be able to apply a very important rule called the empirical rule. We'll be able to compute a z-score and understand what it means. And we're not going to really worry about the tables of finding z-scores. Our calculator can find our z-scores for us, okay? Our TI-84. So the TI-84 has basically rendered a lot of the tables, if not most of the tables, in the appendix as being obsolete in this day and age because of what our calculator can do for us.
So I have a blank screen. I don't know if anybody else see anything different.
Wait a minute. Hold on a second here. Okay. All right, can you see it now?
Yes.
Okay. I got to double check something quickly. All right. All right, so we can see the screen, correct? All right. Okay, so this is what we hope to accomplish in this section here, 11.6. A wide variety of quantities in the real world, like the sizes of individual in the population, IQ scores, and many others tend to exhibit the same phenomenon, which we see that the largest number of have values somewhere in the middle of the range in the classes. So in other words, what this is trying to say, ladies and gentlemen, is that a lot of the natural phenomena can be normally portrayed or is normally distributed. For instance, when I was teaching a stats course many years ago at Baker College, I had my students go outside for a lab and measure pine needle lengths on a pine tree. And I told them to, make sure that they get a good sample and measure all around the pine tree. They brought those links into the classroom and then built a frequency histogram. And would you believe that the links of those pine needles on that pine tree, the histogram that we built, was symmetric? It was a symmetric histogram. And it was bell-shaped, okay? We say the data is normally distributed if its histogram looks like this. Isn't that amazing? So nature seems to love normality for some reason. All right, it loves symmetry. Nature is highly symmetric. You look at our bodies, ladies and gentlemen. I mean, the human body is what? Symmetric. You put an axis right down through the middle here, we have perfect symmetry. Our planet is symmetric. All right. Nature has taught us symmetry. On one end of a fireplace mantle, we put a candle. Nature has shown us that it seems natural, do you agree, to put a candle at the other end? Symmetry. So nature loves symmetry. Why? I don't know why. But trees grow symmetrically around their what? Around their trunks. Do you agree? Why don't they just grow on one side? Why do they grow symmetrically? Why does nature love symmetry? Very deep questions to maybe ponder. Because nature loves normality and symmetry, the normal distribution is a very important probability distribution to touch base with in statistics or probability. And this is what normal distributions look like. Any frequency histogram for any data set collected out in the field that exhibits this structure is said to be normally distributed or bell-shaped. That's what we call a normal distribution signature. And like I said, not only the lengths of pine needles, but if you were to basically record the heights of, let's say, 1 million human beings, ladies and gentlemen, in inches, and build a frequency histogram of those 1 million data points, I guarantee you that it would be a normal distribution. Nature seems to love normality. Okay? Don't know why, but it's a fact. It's a fact all around us. All right. And so therefore it is called a normal probability distribution. It is a continuous distribution in the sense that this curve has no breaks or jumps or gaps in it. So it's a continuous distribution. Another note is that this distribution is also asymptotic. with respect to the horizontal axis, in the sense that this graph approaches the horizontal axis closer and closer and closer and closer as you go far to the right on the horizontal axis, and the graph gets closer and closer to the horizontal axis the farther you go to the left on this horizontal axis. We call this horizontal axis a horizontal asymptote. I don't know if you've ever seen this word before. Asymptote. The P is silent, right? Horizontal asymptote. Has anybody in any algebra course ever worked with a vertical or horizontal asymptotes with the graphs of functions before? Anybody? Have you ever seen this word before? Anybody? Anybody ever see that word before? Asymptote. Well, anyways, this graph is asymptotic. It approaches this horizontal axis and gets infinitesimally closer and closer to it the further you go to the right or to the left on the horizontal axis there. So that's a characteristic of all normal distributions. Okay. All right. Notice the graph will never touch or cross the horizontal axis, though. It'll never touch or cross it anywhere. All right, here are some properties of a normal distribution. The value in the middle of the distribution, which appears most often, is the mean. In fact, ladies and gentlemen, because our distribution is normally distributed and perfectly symmetric, the mean, median, and mode are all equivalent to each other. So the mean, median, and mode of a perfectly normally distributed data set are all equivalent to each other and right in the middle, found right in the middle here. That's an interesting facet. The distribution is symmetric about the mean. This means that, if you were to fold this graph about this vertical dashed line, the curve on the right would mesh up perfectly with the curve on the left. We call that symmetry with respect to this vertical dashed line here. Perfectly symmetric. All right. Number 3, the area underneath this curve, les amis, represents percentages or probabilities. All right. So the area underneath this entire curve is 1, which 1 is what percent? If you have one whole of something, you have what percent of that something? What do you got?
100.
100%. So 100% of the area of this entire curve is found from negative infinity up to positive infinity. So if you go to the left on the x-axis, the horizontal axis forever, to going to the right on this horizontal axis forever, we call that from negative to positive infinity. You're looking at 100% of the area of the curve. So I have a question for you. What percent of the area of the entire curve would be found from the mean, mu, to positive infinity? What percent of this area of the entire curve would we be looking at? What do you think? Anybody? In other words, what's the area of the upper half of this curve? What do you think? What percent of the area of the entire curve is represented by the upper half of this curve? What would be your guess? If the entire area is 100%, what would be the area of the upper half? Upper half. What do you think?
25%.
50%.
What's half of 100%?
Oh, 50. Okay, I thought you said upper half.
That would be the area underneath the upper half of the curve. Therefore, the area underneath the lower half of the curve would also be what? 50%. Is this making sense here? By perfect symmetry. Okay. And the total area underneath the entire curve is 1. All right. And this graph below shows a normal distribution for the heights of women in the United States. Here we go, ladies and gentlemen. I said this earlier, that if you were to go out and measure the heights of all women in this country, and then build a frequency histogram of all those heights, maybe in inches or feet or however, whatever units you use, doesn't matter. I guarantee you that frequency histogram is going to be normally distributed. bell-shaped, normally distributed. So you can see how nature opts for normality in our everyday lives, okay? And this is not just for the heights of people. This is also true for a lot of things in nature, like I said. I mean, if you're gonna measure the lengths of pine needles on a pine tree, I guarantee you the histogram would be bell-shaped and normally distributed like this. Nature seems to, for some reason, love normality. All right, so the numbers on the horizontal axis are heights in inches, and some areas are labeled for reference. Okay, so the middle height is what? Now, this cannot be feet. It's obviously, it's not feet. So what would be your guess these units are here? The units are probably in what?
Inches?
Probably, I would think inches. You know, 63.7 inches is what? A little taller than what? 5 feet, do you agree? 5 times 12, 5 feet times 12 inches per feet would give you 60 inches. So it looks like the average height of all the women in this country is just a little bit over 5 feet. That's the average, the mean of all heights. Okay. That's not saying there aren't any taller women than that. There are. There's a lot of them. There's a lot of shorter women than that, too. All right. The heights are normally distributed. And so, ladies and gentlemen, you see this dark blue shaded region here. This represents the area underneath this normal distribution curve from 63.7 inches to 66.0 inches. So what does this area represent? Well, areas are equal to probabilities. So if X represents the height of a woman, then we would say the probability that the height of a woman lies between 66 inches and 63.7 inches, we would say that probability is about 30%. So about 30% of all women in this country have heights that range from 63.7 inches to 66 inches. Only about 3.4% of the women in this country have heights that range between what and what? 59.1 inches and 57.4 inches. Only 3.4% of the women in this country have heights that range in between these two values here. You're probably wondering, how do they compute the area underneath this curve here? You know, in geometry, basic geometry, we do have formulas for heights of various shapes. For instance, how would you find the area of a rectangle? Anybody remember the formula? The area of a rectangle? It's length times what? Length times the width?
Length times height.
Or length times height, length times width. Bottom line is the product of two dimensions of the rectangle. But ladies and gentlemen, if you look at this shaded blue solid region here, does this look like a shape that's familiar to all of us? With this, especially with this top boundary that is in the form of a curve? Do you think there's a geometric formula that can compute this area directly of a shape that looks like this? The answer is no. No, there isn't. And so how do they compute the area between 63.7 and 66 inches underneath this normal distribution curve? Well, what they do is they use integral calculus, ladies and gentlemen. They use integral calculus, and what they do is they inscribe a whole bunch of real small little rectangles in this region, a whole bunch of them. So they fill out this entire region with a whole bunch of rectangles in here. They're even smaller than what I'm drawing, trust you me, a lot smaller, okay? In fact, they allow the widths of these rectangles to actually approach 0. And it's this limit as we allow the rectangular widths to approach zero that allows for us to inscribe an ever increasing number of smaller width rectangles to fill out this entire region. And then they add up the areas of all those infinite rectangle areas. They add them all up, all the areas of these infinite rectangles that are inscribed as in this region. And voila, you get the area of the solid region. That's called integral calculus. That enables you to do that. But we're not going to do calculus in this course. This is not a course in calculus. This is a course in basic statistics and probability. So how are we going to compute these areas here? Well, to the rescue, we have a wonderful function on our TI-84 calculator called the normal CDF function. Now, what does that even stand for? Well, normal stands for the normal probability distribution. CDF stands for cumulative. D stands for distribution. F for function. So this is the normal cumulative. What does it mean to cumulate or accumulate? This is the cumulative. So that's C-U-M-U-L-A-T-I-V-E distribution function. All right. And this wonderful function that's built into our calculator will enable us to compute the area underneath this normal distribution curve between any two values on the horizontal axis. So it'll enable us to compute the area underneath this normal distribution curve on this interval. We call this an interval. Okay. So that's a wonderful function that's built into our calculator. In the old days, before we had this on our calculator, we had to use the table in the back of the book, the standard normal probability distribution table in the back of our book to compute areas underneath this curve between any two values on the horizontal axis. But we don't have to use that table anymore. This normal CDF is going to supplant the table. Okay. All right, we'll be looking at that in the near future here. And so therefore, I already went over this. That says for B, what percentage of women are between 57.4 and 59.1 inches? That would be about 3.4% of the women in this country. About 30.3% of the women's heights lie between 63.7 and 66 inches. Now, if there are 31,806 women at a stadium concert, how many of them would you expect to have heights that lie between 63.7 and 66.0 inches? Well, we would suspect that about 30.3% of the women would have that height. So to find out how many of these women would have that height, we would take 30.3% of this number. That is to say, you would take 0.303, 30.3% as a decimal, and you would multiply it by the total number at this stadium, the number of women. Get on your calculator and dial it up. You tell me about how many of these 31,806 women would have a height that lie between 63.7 and 66 inches. Round this off to the nearest whole person. So how many of those women would be expected to have a height between those two values? According to this normal distribution of all heights of all women in this country. Right. We would suspect how many women? Please do round it off to the nearest whole person. There's no such thing as a fraction of a person. We would suspect that about 9,000.
637.
9,637 of these 31,806 women would have a height between 63.7 and 66 inches. And we would be pretty darn accurate in saying that. Isn't that amazing? Well, all right, we wouldn't even have to go out and measure all those women. We could just, use the results from this normal distribution study of all heights and just do the simple calculation to determine that. All right, so that's amazing. What a time saver, huh? And this is basically kind of going over what I already talked about here. Okay. And so we would expect about 9,600 and 37 women to have a height between 63.7 inches and 66 inches. Now, ladies and gentlemen, this is the empirical rule. It says when data are normally distributed, and that's the key assumption, your data has to be approximately normally distributed. Approximately 68% of all your data values are within one standard deviation of the mean, and approximately 95% of all your data values are found within two standard deviations of either side of your mean. By the time you venture three standard deviations either side of your mean, that would encompass about pretty much all your data, about 99.7%. Some stats books say 99.9%. Some books just say 99%. So there's a little bit of wiggle room there. By the time you go three standard deviations either side of your mean. So this is the almighty empirical rule. It is called the empirical rule. Sometimes it's called a 68%, 95%, 99% rule. If X bar is the average or the mean of a data set and S is the standard deviation of that data set, then the empirical rule guarantees that in this interval here, from one standard deviation below your mean to one standard deviation above your mean. In other words, the lower limit of this interval is the mean minus one standard deviation. The upper limit of this interval is the mean of the data set plus one standard deviation above your mean, plus one standard deviation. So within this interval between one standard deviation below and one standard deviation above your mean, the empirical rule guarantees that 68% of your observations will fall in between these endpoints of this interval. By the time you venture two standard deviations either side of your mean, from two standard deviations below the mean all the way up to two standard deviations above your mean, in this larger, wider interval, the empirical rule says about 95% of your observations will fall. By the time you venture three standard deviations either side of your mean, from X bar minus three standard deviations all the way up to X bar plus three standard deviations, the empirical rule guarantees that about 99.7% of your observations will lie in between those two endpoints of that very wide interval there. So this is the empirical rule. And because this curve is perfectly symmetric, I can say that about what percent of my data values will lie between the mean and one standard deviation above the mean. You would say what? What's half of 68%? 34%. Do you agree? And notice 34% of our observations would be found from the mean down to one standard deviation below the mean. About 13.5% of our observations would be found between one standard deviation above our mean to two standard deviations above our mean. In this little interval here, we would expect 13.5% of our data values to fall. But ladies and gentlemen, percents are equal to probabilities. That's what we need to understand. Percents are the same thing as probabilities, or proportions, if you will. And you know what probabilities and percents are equal to? They're equal to areas underneath this normal distribution curve. So areas are the same thing as percents or probabilities or proportions. So therefore, the probability that a data value will fall between X bar minus S to X bar plus S, that probability is 68% or 0.68. The probability that a data value will fall between the mean minus 2 standard deviations to the mean plus 2 standard deviations is 95% or 0.95. The probability that a data value will be found between the mean minus 3 standard deviations to the mean plus 3 standard deviations is about 99%, give or take some change. Okay. So I have a question. What's the probability that a data value will fall between 3 standard deviations below our mean to 2 standard deviations below our mean? Anybody hear what I said? What's the probability that we would expect a data value to fall within the interval from 3 standard deviations below our mean to 2 standard deviations below our mean? You would say that probability is what? What would be that probability?
2.35%.
Yep, that's it. Only almost 2.5% of your data, only 2.5% of your data about will lie between 3 standard deviations below your mean to 2 standard deviations below your mean in that little small interval there. This area of the constitutes only about 2.5% of the entire area of this normal distribution curve. That's it. So are we understanding what this empirical rule is telling us, ladies and gentlemen? It's giving us a percentage breakdown, if you will, as to, how our data would be distributed about the mean of this normal distribution. Okay, that's what the empirical rule is telling us. So it's a very useful rule. And this is the rule that governs our ability to build confidence intervals and to also build or also to conduct hypothesis testing. And that's something you'll look at if you take a course in elementary statistics and probability here at Mock Community College Math 150. I'm sorry, you know what? I think when I said that integral calculus was used to find the areas underneath this curve, I said that's beyond the scope of this course, which is an elementary course in probability statistics. I was wrong, ladies and gentlemen. I was thinking that it was my Math 150 section. This is not a course in elementary probability statistics. This is, Math 115, not Math 150. Yeah, Math 150 is the formal elementary course in probability and statistics here at Mock Community College. In that course, you will learn how to use this empirical rule to conduct hypothesis testing for an unknown population proportion or mean, and also how to build confidence intervals and what confidence intervals can tell us about a parameter of a population. All right, but nonetheless, it's important that you see this even in this course. It's a very important rule here, all right? And like I said, the quality control in industry makes use of this normal distribution to make sure that, parts that are coming off the line are within specifications. For instance, let's say like a machine is manufacturing ball bearings all day long. And what are ball bearings used for in the real world? Anybody? Are they important or not? Ball bearings.
Oh, they're
What's that?
very important.
They're extremely important. Can you give me an example of an application for ball bearings? Well, if you can, I can. Ladies and gentlemen, we all drive an automobile of some sort. Do you agree? Well, all of our automobiles or trucks or whatever we're driving have ball bearings. Ball bearings enable your tires to turn about the axle of your vehicle. And ball bearings help to minimize friction. And minimizing friction is a good thing because friction equals heat. And heat starts to break down metals. And once you have a total breakdown, if your ball bearings fail on your vehicle, you can have metal on metal, and then your wheel can seize up. Can you imagine going down the road, the expressway 70 miles an hour, having your wheel seize up on you? Talk about a rollover catastrophe. You could lose your life. Speaking of that, my vehicle has a bearing problem on the passenger side. It's a loud humming sound when you get it up about 45, 50 miles an hour. The bearing has to be replaced. And if I do not replace that bearing, eventually it's only going to get worse. And like I said, you then run the risk of having your tire literally fall off when you're driving down the road. And that's a scary thought. Yes, ball bearings are used in cars and trucks and diesel locomotives. They're used, ladies and gentlemen, in your shopping carts. You go to Myers or Walmart's or wherever you shop, you're pushing around a cart. You have ball bearings in the wheels. They enable the wheels to turn, okay, with a minimum amount of friction. Ball bearings are critical in our everyday lives, all right? So anyways, getting back to this quality control, I don't know if you're aware of this or not, but when parts come off a machine in the factory, there are no two parts that are manufactured perfectly the same. In other words, just say a machine cranks out 1 million ball bearings in a shift during a day or a night. All of those ball bearings have slightly different diameters. All of them do. But as long as those diameters are within tolerance, okay, they are considered to be shippable to the vendor, the customer. As long as those ball bearing diameters stay within like maybe 1 standard deviation below the mean diameter or 1 standard deviation above the mean diameter, they're considered to be okay. But as soon as your ball bearing diameters start to wander beyond this interval, in other words, if you have a ball bearing, okay, whose diameter starts to become like 2 standard deviations below the mean acceptable diameter or 2 standard deviations above the mean acceptable diameter, then we got a problem. Your customer's going to reject the lot. They're going to throw them right back in your face and say, you know, get it right. And if you don't get it right, you're going to lose customers. You lose customers, you're going to go out of business. Okay. So quality control is the last line of defense for any company before the product goes out to the customer. And so you got to make sure that your product is within acceptable specifications. If it isn't, it will be rejected. And like I said, you either make adjustments or else you're going out of business. So quality control is critical in industry, and the normal probability distribution is used in quality control, okay, to build what are called X-bar charts, X-bar charts. Anybody that's maybe ever worked in quality control, maybe you're somewhat familiar with this normal distribution or have seen it, but it is used. So there's a lot of use to this wonderful normal distribution and this empirical rule. All right, let's see what else we got here. All right, now according to a website, answerbag.com, the mean height for male humans is 5 feet 9.3 inches, with a standard deviation height of 2.8 inches. If this is accurate, out of 1,000 randomly selected men, how many would you expect to be between 5 feet and 6.5 feet? I'm sorry, be between 5 feet 6.5 inches and 6 feet 0.1 inches. How many of these 1,000 men would we expect to have heights between these two values here? Well, the given range of heights corresponds to those within 1 standard deviation of the mean. So we would expect about 68% of the men to fall in that range. In this case, we would expect about 680, therefore 68% of 1,000, right? 1,000 men surveyed, we would expect about 680 of those men's heights to fall between 5 feet 6.5 inches and 6 feet 0.1 inches. Now, how did they get these endpoints of this interval, this 68% interval here? How did they generate that there? Well, what was the mean of these heights? The mean was what? 5 feet 9.3 inches, correct? 9.3 inches. That's the mean height. And what was the standard deviation? 2.8 inches. Okay, so here we go. How did they generate that 68% interval there? Well, I'm going to show you how. So the average height of all these men is 5 feet 9.3 inches. Standard deviation is 2.8 inches. Once you go from 2 standard deviations below the mean, excuse me, 1 standard deviation below the mean, to 1 standard deviation above the mean, the empirical rule guarantees that about 68% of your observations are going to lie between these two endpoints. So let's find these endpoints. What would be 1 standard deviation below our mean here? Well, our mean height is 5 feet 9.3 inches. But ladies and gentlemen, this is awkward to have feet and inches all mixed in here. We need to convert to one unit to make our life easy. Let's go to inches. How many inches are in 5 feet? How many inches are in a foot? There's 12 inches per foot. So therefore, if you multiply this by 5 feet, the feet units cancel out, leaving us with inches. What's 5 times 12? So there's 60 inches in 5 feet. What's 60 inches plus 9.3 more inches? That gives us 69.3 inches. You agree? So that would be the mean of this distribution, 69.3 inches. Minus, what's the standard deviation? 2.8 inches. So what's 69.3 inches minus 2.3 inches, 2.8 inches?
66.5 inches.
56.5 inches. Up to the mean plus 1 standard deviation, which is to say 69.3 inches plus our standard deviation of 2.8 inches. That gives us the upper end point of the 68% interval, which is to say it would be 72.1 inches, I believe. So therefore, ladies and gentlemen, we would expect that 68% of all men's heights to lie between 66.5 inches and 72.1 inches. And if we surveyed 1,000 men randomly, we would suspect then that 68% of 1,000, which is found by taking 0.68 times 1,000, which is to say 680 of our 1,000 men would have heights that lie between 66.5 inches to 72.1 inches. That's how they got there. You agree?
So where did the percentage come in?
The 68%, that's the empirical rule. The empirical rule says that between 1 standard deviation below our mean to 1 standard deviation above our mean, 68% of your observations lie in this interval. See that?
Oh, okay.
That's where I got that, from the empirical rule. All right. Now I have a question. Of these 1,000 men, how many would we expect to have heights that lie between 2 standard deviations below your mean to 2 standard deviations above your mean? How many of the heights would lie in this larger interval? What percent, according to the empirical rule? 2 standard deviations either side of your mean. The empirical rule guaranteed that what percent?
30%?
No, 2 standard deviations either side of your mean was 95%, right? 95%. So let's find out between what 2 heights we would expect 95% of these men heights to lie. We got to find the lower endpoint of this 95% interval. That's to say that we take the mean of the distribution and subtract off 2 times our standard deviation. What is the mean? The mean height is 69.3 inches minus 2 times our standard deviation, which is 2.8 inches. Now, what's 69.3 inches minus 2 times 2.8? Well, we can dial it up on our machine.
63.7?
Yeah, so 63.7 inches up to the mean plus 2 standard deviations above our mean, which is to say 69.3 inches plus 2 times our standard deviation of 2.8 inches. And what would be that upper end point of that 95% interval? 3 plus
74.9.
Yeah, 74.9 inches. So therefore, we would be confident in saying that 95% of the 1,000 men that were randomly surveyed, or what would this be? what's 95% of 1,000? That's 0.95 times 1,000, which is how many of those 1,000 men? 900.
950.
Yeah, we would expect 950 of these 1,000 men to have a height that lies between what? 63.7 inches and 74.9 inches. We would expect that. Okay. I have a question for you, ladies and gentlemen. In essence, what we just did is we built a 95% confidence interval for the mean height of all men in the country. We're 95% confident in saying that the mean height of all men in this country lie between 63.7 inches and 74.9 inches. Can anybody maybe cite an example as to where this information would be very useful in the real world? I'll give you a hint. It's in designing things, in building things. Where would this be useful in knowing this? Why would we even care to know this? That, 95% of all the men heights out there range between 63.7 inches to 74.9 inches. Why would we even care to know that? Anybody? Can you give us an example as to why this would be important? I'll give you a hint. It's in building things that we all use in our everyday lives. Okay, I'll give you even more pointed hint. In designing and building cars, why would this be important to know this? Or why would it be important maybe if you're designing like an aircraft, like a commercial airliner that we're going to maybe take a ride on to go from point A to point B? Why would it be important to know this information?
Yes, to accommodate for the average person.
There you go. See, if you're going to build a car, like you want to make sure the cabin height, okay, is conducive or within this range. So that, men, when they get in the car, they don't have to lay down or duck. You know what I'm saying? That's critical. You need to know this information. Or if you're building a cabin for an airliner, you need to know about what the height has to be so their heads don't bump into the compartment, storage compartments above. This is important stuff here, critical stuff in designing things. All right. Designing a spacecraft that goes, maybe to planet Mars in the future. You need to know, this stuff here. These averages, so statistics is critical in designing things. And so all this is very, very important here to be able to, determine some very important information here. All right. So now there are an infinite number of normal distributions because there's an infinite number of means, an infinite number of standard deviations that could arise for any sort of data set. But ladies and gentlemen, of the infinite number of normal distributions, probably the most popular normal distribution by far is called the standard normal distribution. The standard normal distribution. So what makes the standard normal probability distribution stand out from, just any normal distribution? Well, here is the thing that defines a standard normal distribution. A standard normal distribution always has a mean of 0. And it also always has a standard deviation of 1. If a normal distribution has a mean of 0 and a standard deviation of 1, it's called the standard normal probability distribution. All right. And you can see here's an example of a standard normal probability distribution where the mean is 0 right in the middle here. That's the mean, X bar. This would be 1 standard deviation above the mean. There's 2 standard deviations above the mean, and there's 3 standard deviations above the mean. Here's 1 standard deviation below the mean, 2 standard deviations below the mean, 3 standard deviations below the mean. The empirical rule percentages still remain the same. Nothing changes. Okay. So this standard normal probability distribution sometimes is referred to as the Z distribution. And it used to be extremely important in the days before we had the TI-84 calculator. Because in the past, to find areas underneath any normal distribution, we had to first of all standardize our observations to conform to the standard normal distribution, so that we could then go in the back of our book and our appendix and use what's called the Z distribution, which would give us areas underneath this normal curve within any interval along the horizontal axis. But the importance of this standard normal distribution has eased over the years, because we now have technology that can help us, find the areas underneath this normal distribution by using a function on our calculator called the normal CDF function. So it used to be very important, but that's lessened a little bit over the years. All right. So that brings us to what a Z-score is. What is a Z-score? Ladies and gentlemen, every data value of a normal distribution has a Z-score. A Z-score basically is the number of standard deviations a data point is away from the mean of a data set. Okay, so again, I'll say it, a Z-score is the number of standard deviations that a particular data observation is away from the mean of the data set. And to compute the Z-score of any data value X in your data set, you basically just take the observation X, subtract off the mean of the distribution, and then you divide by the standard deviation of your data set. That's how you convert X into what's called a Z-score value. And then you'll have an idea as to how many standard deviations X is away from X bar in that distribution. So if a data point is above X bar in your distribution, then your Z-score for that data value would be greater than 0. If a data point is less than X bar in a distribution, then you would suspect its Z-score Z would be less than 0. All right. Okay, so they want to revert back to example 2, where we want to find a Z-score for a man who is 6 feet 4 inches tall and describe what it says. Well, ladies and gentlemen, 6 feet 4 inches would be how many inches? 6 feet is how many inches? 6 times 12 is 72 inches. 72 inches plus 4 inches is 76 inches. So if you're 76 inches tall, you're 6 feet 4 inches tall. Okay. Remember, the mean of our data set of the heights of all men was 69.3 inches, and the standard deviation was 2.8 inches. So what would be the Z-score of a man that has a height of 76 inches? Let's find out. Let's use the formula. Our Z-score would be 76 inches minus 69.3 inches divided by the standard deviation of 2.8 inches. That would be 2.40. What is that saying now? Well, what that's saying is that a man that has a height of 76 inches, his height would be 2.4 standard deviations above the mean height of all men. That's what it's saying. So again, a man that has a height of 76 inches, that height would be 2.4 standard deviations above the average height of all men. That's what it's saying. All right. We've probably all heard of the ACT versus SAT entrance exam for most universities or college. Well, it's usually very difficult to compare the scores of students that took different exams. One year, the ACT had a mean score of 21.2 and a standard deviation of 5.1. That same year, the SAT exam had a mean score of 1498 and a standard deviation of 347. Suppose that a scholarship committee is considering 2 students, one who scored 26 on the ACT and another who scored 1,800 on the SAT. Both are pretty good scores, but here's the question, ladies, on the $1 million question. Who scored higher on their respective exam? Well, right now it's like trying to compare apples and oranges. Do you agree? Because they both have different means and standard deviations. So it's virtually impossible to ascertain who scored higher on the respective exam. Did the person score higher on the ACT or did the person score higher on their SAT? We don't know. And you're not going to know until you level the playing field. The only way you level the playing field is to convert each of these exam scores into corresponding Z scores. And so for the ACT score of 26, they take 26 and subtract off the mean score for that ACT exam and divide that difference by the standard deviation score of that ACT exam. And they come up with a z-score of 0.94. For the SAT student, they take their score of 1800 and convert it into a z-score by subtracting off the mean score for that SAT exam and dividing that by the standard deviation score for that SAT exam. And they come out with a z-score of 0.87. Aha. Now, ladies and gentlemen, who scored better? The ACT student or the SAT student? Which score is further above the mean score for the respective exam? The ACT score or the SAT score? Anybody? Who scored? What's that?
The ACT one?
You're right. The ACT score, is almost one standard deviation above the average score for that exam, whereas opposed to the SAT score is only about 0.87 units above the mean score for that SAT exam. So yeah, it looks like, relatively speaking, the student that took the ACT exam and got a 26 on that exam, they scored higher than the SAT score. And this is something that the committee would want to know if they're going to, award a scholarship. So you got to level the playing field. Z-scores help us to level the playing field and compare two different scores from two different populations, if you will, or samples. So Z-score is very important in that regard. All right. I'm going to show you how to find areas later. We don't have to really use tables in the back of our book there. Okay. I'm going to show you how to do this on our calculator here. In fact, we can start like right now. If you look at A here, they want you to find the area underneath the standard normal distribution curve between z equals 1.55 and z equals 2.25. Let me draw a picture of that so we can appreciate what that's saying. What area are we being asked to find here? Well, it is the standard normal distribution. And because it's the standard normal distribution, what's the mean of this distribution? What does the mean always have to be for a standard normal distribution? Always has to be 0. And the standard deviation always has to be what? 1. Okay. So you know what? Where would 1.55 be? That's saying our data point would have to be 1.55 standard deviations above our mean. So would it be to the right of X bar or to the left? What do you think? To the right or left of X bar, 1.55. Well, 1.55 is greater than 0, correct? So it's going to have to be above here. We'll call that about 1.55. And where's 2.25? Well, that's even further above our mean. 2.25, we'll call it right here. They want us to find the area underneath the standard normal distribution curve between 1.55 and 2.25. In other words, they want us to find this shaded area here. Well, we're not going to do numerical integration, ladies and gentlemen, to determine that. We're going to use our calculator. All right. And here's how our calculator works here. Son of a, are you kidding me? It erased it? All right. Well, anyways, I'll just redraw it over here. 1.55 to what? 2.25, I believe it was. So they want us to compute this shaded area here. All right. How do we do that? We use the normal CDF function. I'll show you where it's at on the. Well, wait a minute. What am I talking about? This is 115. This is not 150. We don't have a TI-84. All right. Okay, so how are we gonna find that area, ladies and gentlemen? Well, it can be done. We do have a table in the back of my book. Unbelievable. When I was teaching this class today, I was under the illusion that I was teaching my stats class 150. I am so sorry. We got to find that area. So how are we going to do that? Well, we have to use the standard normal probability distribution table in the back of our book. So where's that? Well, we got to go to our book, which means that we have to go grab our book. So we go to Alex here, and in the back of your book, there's an appendix, and it should have a standard normal probability distribution table. It does. I'll show you where it is. It's Appendix A. The back of our book, there's on Appendix A. Appendix A. There it is. Areas under the standard normal probability distribution. There's a table. See the table? All these decimals are areas. Okay. But how do we use the table? All right. Now, notice this little picture is very important here because it tells us how our table works. Notice areas underneath the standard normal distribution curve are computed from the mean 0 up to some z-value on the horizontal axis. And so, ladies and gentlemen, what are we trying to compute here? We're trying to compute the area from 1.55 to 2.25. Well, unfortunately, our table doesn't work this way. It doesn't compute areas between two z-values, but it will compute the area from 0 up to a z-value. So here's what we're going to have to do. A little bit of basic subtraction. It's no big deal. We're going to have to do this. First, we're going to have to find the area between 0 and 2.25. We got to find this area first. And then we're going to subtract off the area from 0 to 1.55. And ladies and gentlemen, if I take this area and subtract off this area, what's it going to leave me with? Think about it. If I take this area and subtract off this area, will it not leave me with the area in between these two values? Do we agree with that? If I take this area here and subtract off this area here, that's going to leave me with the area that I want to find. So that's what we're going to do. So what's this area? How much area is between the mean, 0, and 2.25 standard deviations above the mean? We got to go to our table to find that. So how do we find that? Our z-value is what? 2.25? Notice these are the z-values. Where's 2.25? .25. Anybody see it here? Aha! I found it. A z-value of 2.25. What's the area? 0.488. There you go. Write that down on your paper. 0.488. That's this area, 0.488. Now we got to subtract off the area from our mean 0 up to 1.55. We got to find this area using our table. Let's go back to our table and try to find 1.55. Where's 1.55? 1.55. Where are you? Oh, where is 1.55? Ah, found it. 1.55, the area is 0.439. Write that down. Okay, now all we gotta do, ladies and gentlemen, is subtract. And we'll have the area between 1.55 and 2.25. It's that simple. So what is 0.488 minus 0.439? 0.488 minus 0.439. That gives me 0.049. That is this area right here. Okay? That's the area between 1.55 and 2.25. Everybody see how I used the table to find that area? The standard normal probability table in the back of your book, Appendix A, was needed. Now, when you get into probability statistics, you're not going to need that table because you'll be able to use a TI-84 calculator. The TI-84 calculator has a normal CDF function built into it, whereby it can compute your probabilities straightforward. You don't have to even dabble with any of that. All right. Okay. So we understand how that was done there. All right, let's go back to that PowerPoint presentation. Now, here's a question. How would we do this one? How would we do B? How would you find the area between -0.6 and -1.35? Well, I strongly recommend that you draw a picture of this so that you have an idea as to what area you're trying to find. That's going to help immensely as to how you're going to go about finding it. Again, we're using the standard normal distribution where the mean is 0. Where would be -0.60? Well, that's going to be just to the left of your mean 0. -0.60. And -1.35 is going to be further to the left of your mean. And so here we go, ladies and gentlemen. B wants us to find this area underneath our standard normal distribution curve between -0.60 and -1.35. How are we going to use the table to find that area? Does our table even allow for negative z values? Does it even allow for negative z values? Oh, no. I don't see any negative z values. Do you? Does that mean we're screwed? No, there's a way. The way, ladies and gentlemen, is to use something called symmetry because this curve is not 100% symmetric. So you know what this is going to be equal to? This is really going to be equal to, by symmetry, it's going to be equal to the area from positive 0.60 up to positive 1.35. Same area by symmetry. Everybody see that there? This area symmetrically is equivalent to this area. Now we showed you how to do this area. We could use our table because this is going to be found by taking the area between our mean 0 and 1.35, excuse me. We're going to use the table to find this area, and then we're going to subtract off the area from the mean 0 up to 0.60. And when you take this area and subtract off this area, you're going to be left with this area, which is equivalent to this area. So let's go to our table and find this area. 1.35. Where is 1.35? Calling all cars. Where's 1.35? Aha, I think I found it. Right here. So what's the area? 0.412. Write that down. 0.412. 0.412 is this area. Now we got to go find the area between 0 and 0.6. Where's 0.6? Oh, found it. 0.6 is right here. The area is 0.226. Write that down. And then we're going to subtract off these areas, ladies and gentlemen. And we're done. We just have to subtract this area off from this area. And we really have this area, which is equivalent to the original area they're asking us to find. So we might have to just work around a little bit using our table because it only works one way, this table. But it's really no big deal. As you can see, it's easily doable. And so this area is gonna be equal to 0.186. That is the area that they were originally asking us to find. Is this making any sense how we're doing this here? Using our table, our standard normal table, how we're computing areas between two z values on the horizontal axis. All right. You see how that's done? All right, so ladies and gentlemen, therefore I want you to do this one for classwork number 1. Everybody, I want you to find the area between 1.50 and negative 1.75. And I'll even draw it. I'll even draw what it looks like, what area they want us to find here. So using your normal table, your standard normal table in your appendix A, remember the mean for the standard normal distribution is always 0. So 1.50 is going to be up here somewhere. And negative 1.75 is going to be down here somewhere. Would you know how to find this area, ladies and gentlemen? You going to know how to do that? Well, I'll tell you how it can be done. I'll give you a jump start. First, you might want to find this area here. From 0 up to 1.75, positive 1.75. This area, ladies and gentlemen, right here, is equivalent to this area right here by symmetry. Isn't that true? By symmetry? By symmetry. And then once you find that area, you're going to add it to this area. You're going to add it to the area from 0 up to 1.5. There you go. So when you take this area and add it to this area, you have the area of this, what they were originally having us find, between negative 1.75 and 1.50. Go ahead, use the table and compute that area. Classwork 1. Okay. Did anybody find the area from 0 to 1.75 using the table in Appendix A? Anybody? What's this area right here, this red area here? What's that area?
0.460.
0.460. Can anybody confirm that? Anybody? Do we have a confirmation on that number?
That's what I got.
Okay, now, using that same table, did you find the area from 0 to 1.50?
Yeah, 0.433.
0.433. Any confirmation on that number? All right. I'm assuming those are correct until, I don't know. Let me know if anybody got anything different. Anyways, you add those together and you get 0.893. 0.893, therefore, would be the area, okay, between negative 1.75 and 1.50. That would be the area. In other words, we would expect about 89.3% of our data values to fall between 1.75 standard deviations below the mean to 1.5 standard deviations above the mean. And that's true for any normal distribution, not just for the standard normal distribution. Okay. Again, we would expect about 89.3% of all normally distributed data values to lie between 1.75 standard deviations below the mean to 1.5 standard deviations above the mean. All right, so that's pretty amazing stuff here. This table is helping us out to compute probabilities underneath the standard normal distribution curve here. And this is just going over, drawing a picture and going through everything I already went through there. Okay, so that's just the solutions of everything that's going on here. Okay. And it looks like those values are correct, 0.460, 0.433. Thank you for those. All right. Okay. Classwork number 2, I want you to do these problems right here. Using symmetry and using the Appendix A standard normal probability distribution table, I want you to find these areas to the right of z equals 1.70 and to the right of z equals negative 0.95. Go ahead and do that, classwork number 2. Oh, by the way, you might want to draw a picture. For instance, like for A, draw a picture of the area that you're trying to find, that they want you to find. It helps. Here's the mean of 0 right in the middle. And 1.70, standard deviations above the mean's got to be, up here somewhere. 1.70. They want you to find the area underneath this entire curve that lies just to the right of 1.70 to positive infinity. They want you to find that area there. How in the world are we going to do that? Your table doesn't work that way. Your table only works from 0 up to a z value. Do you agree? Does anybody know how we can find this upper tail area here? Tell you what, can we find this red area by using our table? Can we find it? Yes, we can. And if we find that red area, how are we going to find the blue area then? What are we going to do? Think about it. What area of the entire curve lies above the mean? What percentage? The upper half. Oh, there's your clue. There's your clue. Upper half. What's half of 100%?
50%.
50% of your area lies above the mean. So here's all you got to do. You just got to find the red area using your table and then subtract that from what? Subtract that from 50% or 0.50, and you'll have the area of the blue shaded region. There you go. Go ahead and finish that problem and do B. I'm going to let you try to do B all on your own. Remember, symmetry is the key. All right. Try that out. All right, so this first one here, you want to find the area to the right of z equals 1.70, which means this blue shaded upper tail area. That's going to be equal to the upper half area of the curve, which is 0.500, minus the area from 0 to 1.70. Because if you take the upper half of the area of the curve and subtract off the area from 0 to 1.70, that's going to leave you with the upper tail blue shaded area that we want to find. So what is the area between 0 and 1.70 from the table? It should be about 0.455. Subtract that from 0.500, you get 0.045, and that'd be your answer. So therefore, that is going to be this area here, okay? Or that's going to be the probability that z is greater than 1.70. That's saying the same thing as the area to the right of 1.70. So the probability that z is greater than 1.70 would be 0.045. Because remember, areas are the same things as probabilities. Area and probability are the same thing underneath these normal distribution curves. Now to find the second one, the area to the right of z equals negative 0.95, I worked that out here. We got to find all this area here to the right of negative 0.95. Well, we can do so by symmetry. And the fact that the area of the upper half of the curve is 0.50. So this area of the upper half is 0.50. And if you take this area and add it to this area, you'll have this area. But our table cannot find this area. So by symmetry, this area is really this area from 0 up to 0.95. And then you can use your table. From 0 to 0.95, you find the area is 0.329. Add that to 0.500, and you get 0.829. Did anybody get these areas here that I showed you? Did anybody come up with any of these areas here?
Yeah, that's what I got.
All right. This is showing you the normal CDF function, but that's on the TI-84 calculator, ladies and gentlemen. You don't have to go out and buy a TI-84 calculator. All right, let's go to our book. We don't have much time left. I just want to see if there's any problems that we haven't covered yet that we could maybe look at. So this is a section 11.6. Where are we? 11.6. Here we go. Yeah, normal distribution. As always, you're welcome to look over these sections and, you know, maybe work out some supplemental examples or things like that. All right, let's go down here. Okay. All right, now, and so as I'm number 13, I will work this problem out. They want you to approximate the number of data values of the 50 observations that fall within the range of 10.5 to 13.5 for this normal distribution with a mean of 12 and a standard deviation of 1.5. I'm going to work this problem out for you. Number 13 in your textbook. All right, so therefore, we know the mean of this distribution, x bar is 12, the standard deviation, lowercase s, is 1.5. They indicate that there is 50 observations, and of the 50 observations, how many fall within the interval of 10.5 to 13.5? Okay. All right, this is problem number 13 in our textbook here. You can even draw a picture of this normal distribution here. The mean is right in the middle, which is 12. 10.5 is less than 12, so that's going to be down around here. I'll say that's about 10.5. And 13.5 is greater than 12. I'll put it over here about. Here's what they want you to do, ladies and gentlemen. First of all, we got to find the area between these two endpoints of this interval. We got to find this area here. But this is not the standard normal probability distribution table, standard distribution, because the mean is not 0. So we cannot just take this to our table in Appendix A yet. We can't do that yet. All right. So how are we going to do this problem? Well, here's what we first of all have to do here, ladies and gentlemen. We have to standardize 10.5 and 13.5. In other words, we got to find the z-scores for these endpoints of this interval. So what would be the z-score for 10.5? Well, we use this formula, which is to say x minus x bar divided by the standard deviation. So what is x? X is 10.5 minus the mean. What's the mean of this distribution? The mean is 12 divided by the standard deviation, which is 1.5. Get on your calculator and dial this up. What's the z-score for 10.5? In other words, how many standard deviations away from the mean is 10.5? That's what we're about to find out. Oh, it's -1. So that means that this observation is 1 unit below, 1 standard deviation below the mean, 10.5. Now we got to standardize 13.5, the upper endpoint of this interval of interest. So what's the z-score of 13.5? We put 13.5 in for x. Subtract off the mean of this normal distribution, which happens to be 12, divided by the standard deviation of this normal distribution, which is 1.5. What's the z-score of this upper endpoint? Oh, that happens to be 1 standard deviation above our what? Our mean. Do you agree? So, ladies and gentlemen, what do you think? Isn't this observation 1 standard deviation below our mean, and this observation is 1 standard deviation above our mean? What does the empirical rule predict would be the percentage of observations that lie in that interval? Do you remember from the empirical rule? 1 standard deviation either side of your mean in this interval. The empirical rule predicts that we will have what percent of our observations?
68%?
68%. That's the area of this shaded region. It's 68%. Because these endpoints are 1 standard deviation below to 1 standard deviation above our mean. This is the 68% interval. So in other words, of these 50 observations, we would expect 68% of them to lie between 10.5 and 13.5. Well, how many is that? Well, to answer that question, we have to take 68% of 50, which means you turn this into a decimal as 0.68 and you multiply it by 50. You have your answer. So what is 68% of 50? 34. So therefore, 34 of these 50 observations will have a value that lies between 10.5 and 13.5. And we're done with that problem. Everybody understand how I just did that problem there? You see, ladies and gentlemen, we had to de-standardize these values, or excuse me, we had to standardize these values, turn them into z-scores so that we know, how many standard deviations away from the mean they are, so that we could then tap into the empirical rule, okay? The empirical rule. So the empirical rule is very important. So that's what we have to do. We may have to convert our observations or endpoints of our interval in question into z-scores in order to compute the percentage of observations that lie between the endpoints of that interval. All right, let's see if we can do another problem here. Okay, let's see here. And that's how all these other problems are going to be done too. Okay, they're all done the same way. You're going to have to turn these values of these endpoints of this interval into z-scores. Okay, find the area underneath the standard normal distribution curve. Now, this is just finding areas underneath the standard normal distribution curve. And again, you would use that table in Appendix A. All these problems are done the same way, but I strongly recommend you always draw a picture of the area you're being asked to find. Very important. It only facilitates your ability to know how to find that area with the table, because sometimes you have to maybe use the property of symmetry And you have to understand whether you have to add or subtract area. So it's very important to always graph the area between the two z values they want you to find. Very important to do that. Okay, let's see. Is there anything else here? Okay, in order to students 206. All right, I'll try another problem here, number 47. The College Board reported that SAT scores in the early 2000s were normally distributed with a mean of 1,026 and a standard deviation score of 210. A, what percentage of the students scored over 606? B, out of 500 students, how many scored between 816 and 1236? All right. So therefore, ladies and gentlemen, in order to do this problem, we're going to have to level the playing field. We're going to have to turn these values into z-scores because I can't tell heads or tails as to how many standard deviations these things are about the mean. For one thing, our SAT scores are distributed according to the normal distribution. What was the mean? What was the mean score? 1026. And what was the standard deviation score? It was 210. For question A, they want us to determine what percentage of students scored over 606. Over 606. Got a question for you. If this is the mean, the 1026 in the middle, where would be 606? Would it be to the left or to the right of the mean? Where would be 606? Left or right? This is 1026. Where's 606? To the right or left of the mean?
Right?
Well, it's got to be less than, 606 is less than 1026, correct? So it's got to be, somewhere down here. They want to know what percent of the students scored above 606 on this SAT exam. In other words, when they say what percent, they want to know what area. Percent is the same thing as area. We got to find this shaded area here. That's saying the same thing as finding the percent or the proportion of students that scored more than 606 on this SAT exam. Well, how are we going to find that area? Unfortunately, ladies and gentlemen, we cannot take this to table in Appendix A yet because this is not the standard normal distribution. This is a normal distribution, but it's not the standard normal distribution because the mean is not 0. So what do I have to do with this 606? I have to turn it into what kind of a score? I have to standardize it, turn it into a what score? What's that called? A
Z-score.
Z-score. We got to turn 606 into a Z-score. To do that, we take 606, subtract off the mean of this normal distribution, which is 1,026, and we divide that difference by the standard deviation, which is 210. Get on your calculator and dial that up. And we will have converted this into a z-score that will tell us how many standard deviations this score is away from the mean of all scores. Oh, that's -2. So, ladies and gentlemen, that shows me that this is 2 standard deviations below the mean. This is 2 standard deviations below the mean. Okay. So this is going to be X bar minus 2 standard deviations. It's 2 standard deviations below the mean. Everybody see that there? So using the empirical rule, can anybody tell me what percent of the entire area of this curve lies above 606 here? Well, how can we find this area? Well, here's how. We know that this at least is the area of the upper half of the curve. Do you agree? It's the upper half area. Plus, oh, it's not just that. Plus, there's more area to add to this, though. The area we got to add is from the area from 0 down to what? -2. Because, ladies and gentlemen, I know this is 2 standard deviations below my mean. So if I convert this now to the standard normal probability distribution where the mean is 0, we can now use our table in the back of our book. Because this has to be -2, 2 standard deviations below the mean. So do you agree if I take this, if I find this area and add to it this area, it's equivalent to as if I what? Have this area. Isn't that true? Is this making any sense? If I take this upper half area and add to it this area here, it's equal to this area here. Isn't that true?
Yes.
But ladies and gentlemen, our table doesn't work this way from 0 down to a z value. It only works from 0 to up to a z value. So by symmetry, what is this area really equal to by symmetry? Well, by symmetry, this area is really equal to what? This area, from 0 up to +2. Now, go in your table. Find me what this area is here. What area lies between 0 and +2 underneath the standard normal probability distribution? Appendix A. Lay down. What area is that from 0 to 2? Can we read off that area? I know this is 50%. This is the upper half area here. This is 0.50. But what's this area? 0 to 2. I don't know. Well, I do know what 2 standard deviations either side of my mean according to the empirical rule. 95% of my observations lie. So what's half of 95%? Oh, that gives me 47.5%. So therefore, this area is going to be 0.475. Isn't that true? So what's 0.500 plus 0.475? That's 0.975. So ladies and gentlemen, 97.5% of the scores were higher than 606. Let me write that down. 97.5% of all scores on this SAT were higher than what? 606. So what percent of the scores were lower? So 100% minus 97.5% is what? So 2.5% of the scores were lower. So what percentile rank is the score of 606? Anybody? What's the percentile rank? What's the percentile rank of that score, 606, on this SAT exam? Is that a good score? The percentile rank is only what? 2.5%. That means, ladies and gentlemen, that only 2.5% of the scores were lower than ours, and 97.5% of the scores were higher than ours. That's a terrible score. That is a terrible score on that exam. Does that make sense? Awful score. All right. And I have a question for you. Suppose that 500 students took this exam. How many of the 500 students scored better than 606? How would you determine that? If 500 students took this exam, how many of the 500 students scored better than 606? Well, 97.5% of them. So you take 97.5% of 500, that's to say 0.975 times 500. And you would have the number of students out of 500 that scored better than 606. That would be a whopping about 487 students scored higher than your score of 606. That's not good. That's not good at all. That's a terrible score. But does it make sense how we did this problem? How we're using that table in the appendix, how we're standardizing endpoints, turning them into z-scores so we can then tap into the standard normal distribution table in our appendix A. You understand how to do this, ladies and gentlemen? The empirical rule. The empirical rule is also helping us in the fact that we have symmetry that goes to bat for us also with this normal distribution curve. Symmetry is very important because our table only works one way. So we're at the mercy of, symmetry to help us out here. Okay. All right, I will open up everything that I mentioned. I'll get that all open. If you want to work ahead, complete the course before Tuesday, go ahead. If you want to wait for the last section for me to formally go over it on Tuesday, by all means, be my guest. Whether you show up or not on Tuesday, ladies and gentlemen, I gotta show up, all right? That's my last lecture on Tuesday on 11.7.
Don't say nothing.
All right, you all have a great weekend and stay on the line if you have any questions.
Hello?
Yeah, what's going on?
Okay, because I was just letting you know the